Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 1. Lagrange Polynomials and Lagrange Interpolation. Lagrange interpolation is a method for estimating a polynomial that passes through a given set of points. Given a set of known data points, the Lagrange polynomial provides an exact polynomial that intersects all of the points, making it useful for interpolation tasks. Lagrange polynomials are widely used in data fitting, estimating unknown values between known data points, numerical integration, approximating integrals of functions, curve construction, drawing smooth curves that pass through a set of data points. Consider a polynomial that passes through n+1 discrete data points, which may not necessarily be uniformly spaced, which are called interpolation points. Then, an nth-degree polynomial, such as this one, which passes through all data points, should satisfy the condition for k equals 0 through n. This condition is used to determine the coefficients, c's, that satisfy the following property. LKX's denote so-called the Lagrange basis polynomials. The Lagrange interpolating polynomial p sub nx, passing through n+1 points, can be constructed as follows. Lagrange polynomials for a set of n+1 abscisses take the following form. Note that LKXI is 0 for k not equal to I and LKXK is 1. The Lagrange interpolation polynomial is unique for a given set of data points. There is a point Cx for any x in x 0 to xn, such that where E in x is the error, defined as the difference between the true and interpolated values. If a discrete function fx is truly a polynomial of nth degree or lower, i.e., fx equals p sub mx, m less than or equal to n, then the interpolating polynomial reproduces the true polynomial, in which case the absolute error is 0 since the n+1 derivative of fc is 0. The magnitude of Lagrange interpolation error is influenced by a number of factors. The length of the interval, x0 to xn. The interval size of the subintervals, delta xk. The position of x in the interval. The degree of the interpolating polynomial, and the number of discrete data points in the set. If an interpolating polynomial is to be used numerous times, instead of applying equation 6.5, it is more convenient and practical to express it in simplified power form. P in x equals a in x to the n plus through plus a1x plus a0, or preferably in the nested form as follows. The advantages of the method are: the method provides an easy and simple way of constructing an interpolating polynomial. It is very easy to adapt to computer programming. It is applicable to both uniform and non-uniform discrete functions. Once Lagrange polynomials are constructed, they can be used with different ordinate sets as long as the number of data points and the abscisses in the set are fixed. The disadvantages of the method are: it is CPU time intensive and impractical for a large data set. Adding new data points to an existing data set increases the degree of the interpolating polynomial, which has to be reconstructed from scratch. Estimating the error bounds of an approximation is not easy. Errors outside the data range increase uncontrollably, which makes the method too risky to use for extrapolations. In the following example, we are asked to derive the Lagrange basis polynomials and the Lagrange interpolating polynomial for the given dataset, and then estimate f 1.2, f 2.5, and f 3.25. We construct the Lagrange basis polynomials according to the following expression. Note that the Lagrange basis polynomial is a product over all the other points except for the one corresponding to k equals 0. Specifically, for L0 we will omit x minus x0 over x0 minus x0. Substituting numerical values, we find L0x as follows. When constructing L1x, we will skip x minus x1 over x1 minus x1. Substituting numerical values, we find L1x as follows. When constructing L2x, we will skip x minus x2 over x2 minus x2. Substituting numerical values, we find. In constructing L3x, we skip x minus x3 over x3 minus x3. Substituting numerical values, we obtain L3x as follows. Finally, we construct L4x in the same manner. We find the Lagrange interpolating polynomial is constructed as follows. Substituting the Lagrange basis polynomials into this expression and simplifying like terms, we obtain a fourth-degree polynomial. If an interpolation polynomial is to be used many times, it is worth taking the time to simplify and reduce this expression to only a single polynomial, as this will reduce the number of arithmetic operations and CPU time. Using the interpolating polynomial 4x equals 1.2, we obtain 3.272064. 4x equals 2.5, we find minus 0.64. 4x equals 3.25, we get 1.44766. If we plot the data points and the interpolating polynomial, we observe that the interpolation polynomial is consistent with the trend depicted by the first 4 data points. Since the interval is relatively large, and also there are no additional data points in between x equals 2 and 3.5, one should be cautious when interpolating for the x values in this range. The true change could be one of the many alternative curves. That is all for now. See you next time with another topic. Bye.